Hi, I'm Akash Doshi, a final year graduate student advised by Professor Jeffrey Andrews, and today I will be presenting a deep reinforcement learning approach for contention-based spectrum access. We now describe our problem statement. Consider a network with n full buffer single input single output links. This means we have n base stations and n UEs with one user scheduled per base station. In this case, the received signal yj of n and the signal to interference ratio, or the SINR, in time slot n and UEJ in the downlink slot n are given as shown. As we can see, there is a signal term and an interference term in the received signal, which is made use of in computing the SINR. The throughput Rjn could then be approximated by the Shannon formula given by W log of 1 plus SINR in the current time slot, given that we assume zero decoding error. The objective of base station I is to choose an action AI in each time slot n, where AI can be 0 denoting no transmission or 1 denoting transmission, with the objective of maximizing the long-term proportional fairness metric given by the sum of the log of the average rates, where we can see that the average rates of the users are given by the exponentially smoothed formula, with B being the smoothing window. If all the base stations were controlled centrally by a proportional fairness-based BS scheduler, then the optimal decision vector A star n would be given by the maximum over all the action vectors of the sum of the rate divided by the average rate. However, the centralized proportional fairness-based BS scheduler requires knowledge of the interference channel matrix in the current time slot, as well as the average rates of the users across all base stations. In reality, we have distributed controls by n base stations, with each having only a partial observability of the environment. Contention-based spectrum access as an LBT makes the base station's choices of action sequential. We capture this sequential nature of transitions in the two-state diagram shown on the left. At the beginning of contention, when each base station has not yet been assigned a counter, we consider it to be in an end-of-slot state. It is then assigned a counter, which expires after the value of the counter decrements to 0, and then it is able to sense the spectrum. This is when we consider to a transition into the CON state with the added side information. The added side information basically comprises of an inter-G0B vector EI theta I that captures the inter-BS energy detected for each ongoing transmission and the counter theta I. We consider that the transmitting base station transmits a unique orthogonal preamble for the remainder of the contention phase once theta I expires. We now describe how the EOS and CON terms can be incorporated in an RL framework. First, we describe how the Bellman equation can be modified for deep Q network-based training. Essentially, we have an alternating update where the label of the EOS state is computed by a maxima of the actions that can be taken in the contention network of the QCon network, while the label of the CON state is computed using the Q output of the EOS network, which does not have any action to choose from. The loss is then simply the mean squared error. On the other hand, we have the generalized advantage estimation procedure used for estimating the target values of the value functions that will be used for PPO. So here we consider an actor-critic neural network architecture with a value function for the EOS state and a pi network and a value function in the contention state, where we will be choosing an action whether or not to transmit. The truncated GAE equations for both states with the GAE hyperparameter lambda are now given below. As we can see, the delta CON term basically alternates between VEOS and VCON, while the delta EOS alternates between VCON and VEOS. Consequently, using the GAE updates, we can easily compute the V-target EOS and V-target CON equations as shown. The results show how both the PPO and DQN based RL algorithms outperform a Gini-aided configuration adaptive ED threshold. As we can see, the cumulative reward earned on both the layouts is higher, and this is reflected in the higher sum rates obtained by both algorithms as compared to the adaptive ED baseline. We can also see that within the increase in inter-base station separation from L1 to L2, more base stations can transmit simultaneously, hence the reward earned and the rate achieved is higher. Moreover, we see that a single standardized threshold of minus 72 dBm cannot provide the same degree of fairness in different scenarios. For example, in L1, the standardized threshold of minus 72 has not even been plotted. Also, this shows that RLPPO shows faster convergence and more stability than RLDQN, and even outperforms DQN in one layout.